we are going to have three speakers talking about three exciting projects this morning. And I will introduce our first speaker, Milan Budahoki. He is a GIS and spatial data librarian at University of Maryland Libraries. He manages GIS and spatial data center located in McLean Library. He provides GIS spatial data services to the UMD community via consultations and instruction. He specialized in GIS analysis, spatial data management, mobile server web GIS, server applications, geospatial big data analytics, and remotely sensed data processing. He's also certified Part 107 remote pilot and has interest in using UAS for on-demand data collection for research projects. They'll be talking about Wayfinding indoor navigation system for McLean Library. Milan, the floor is yours. I will share my screen.
Thank you, Shirley, for the introduction, and good morning, everyone. So I think the slide is on the way. In the day-to-day my work, I do provide GIS and spatial data service to UMD GIS user. I work with a faculty, researcher, student, and other staff, right, who made it GIS service. And so today I'm going to talk about kind of a particular spatial project that we have undertaken in the Megalodon Library. And so I would say like GIS project that we have undertaken in Megalodon in the library. And so it's still a project under progress. And so today I'll be highlighting some of the work we have accomplished so far. And so it's a wayfinding project, right? And so the name itself, it says like we're trying to find or build a indoor navigation to find or help our patrons to find some of the resources within the library, right? And so that could be the resources could be a book, could be a tech service center, could be GIS lab, could be some of the some center-based kind of service, or maybe study rooms and many more. And so so we do work with the campus partner, that's Enterprise GIS team, so who are part of UMD facility management. So they've been with us since day one, kind of brainstorming, setting up the things, and prototyping the ideas, and many more. And so we also have a technical partner with the Arcgis indoor team, and also indoors. That's a company based in Vienna, Austria, but that they are part of ISRI now. So next slide, please. So just to give an idea that University of Maryland Library System has around 8 libraries. And so 6 of them are on campus, and there's 2 libraries that are off campus. And so the Megalodon Library, that's the main library branch. And so that's, you see that number 4 in this picture, that's a location of Megalodon Library. Next slide, please. So Megalodon Library is one of the largest and busiest building on campus. And so the Megalodon Library has has like 8 floors, including 1 basement, and total assignable square footage for the Megalodon Library is 259,000 square foot, was equivalent to 4.5 times the football area of football field. And so the library has more than like 2.5 million of collections, like books, folios, like different medias, and lots of collections, right? And so we are a part of like a federal depository library, and so we house lots of maps, and so we have around 250,000 print maps, and so the building has 100 plus study rooms. Some are individual study rooms, some are quiet study room, some are group study room, some are like family study rooms, and so there are 100 plus office spaces and meeting rooms. And the library also features a lot of other kind of specialized services like text board, equipment loan area, writing centers, and the research common, like some resource support unit. And so like a list goes on and on and on. And so we have lots of other point of interest, like animators, or like a printer, copier machine, scanner, plotters. And so the building itself is huge, and also like there are a lot of resources that patrons if the patron wants to find something that's it's a little kind of challenging in terms of navigation within the buildings or within the floors, right? So next slide, please. So what is the current practice, right? And so how our the patrons have been using, what kind of the tools or techniques they've been using to navigate within the library to find the resources they want within the Megalodon Library, right? And so the very classical example would be like looking at the signage, right? The signage are everywhere. So you see in the hallways, in elevator, staircases, and like some section of the floor. And also like if you want to look really down to like some books, so you can have like a stack number and call ranges. And so that's how they find the resources they want to find in the current scenario, right? And so, yeah, so next page, please, next slide, please. So there's like a little kind of more organized way to navigate within the library. Megalodon Library is looking at the floor maps. And so those are like not georeference map, but it does have like a floor plan as a kind of PDF map. And so it does have some other details that would help like patrons to find some of the things that they're interested, like from books to some of specialized service and some the point of interest. And so maps are usually when patrons walk into the front desk. And so when they talk to like the service expression, and so they will hand a map, a printed map. And so they will just, will have like a self-help kind of guide to find the things that they wanted in certain floors. And so they'll have to like go and find the things, or even the library staff will provide some kind of basic instruction to a guidance to find the things that's located in each floor, or the things that you want to find in a particular floor, right? So next slide, please. So if you're lost with the map, and so there's like live help, and so there's a assistant phone. You can use those phone to call like front desk, and so they will give you a more instruction or maybe guide you to the destination where you want to find certain things. Right? Next slide. So we had a lot of challenge, right? And so we have lots of resources within the library, and so now current practice of navigation is very kind of classical way to look at the signs and look at the floor maps, and so which are very not intuitive or is not efficient way to find certain things in a timely manner. And so we did a kind of some need assessment how we can better provide our users or like patrons to navigate within floors to find certain things, right? And so Wayfinding committee was formed. Then we did a kind of thorough evaluation of what could be the best options or like approach to better serve our patrons to route within the floors or within the building. And so one of the recommendation was like a digital pathfinding. So so we want to build some kind of mobile-based application to find the things that patrons want, right? And so we started partnering with the campus enterprise GIS team. And so that's kind of aligns with their kind of bigger goal to make a smarter campus, meaning that they want to upscale this kind of a navigation, the system for a whole campus. And so the Megalodon Library is being a pilot. So we'll start with like a Megalodon Library. And so we explore like a couple of other avenues, like what could be the best platform to deploy those kind of indoor navigation system. And so we found like probably Arcgis indoor would be one of a good option. And so we approached with the Arcgis indoor, and we got like a technical support, and so we've been working and collaborating with the Arcgis indoor team to set up the system. Next slide, please. So the Wayfinding committee and also library staff, they come up with like a wish list, what they want to see in the application, so that we can better serve our patrons, right? And so it's all about kind of having all resources of having certain kind of the features that would help patrons to better navigate and find the things that are located within Megalodon Library. So the idea would be just to build up in a mobile application and just help them to route from anywhere from campus or from anywhere within the floors, right? So next slide, please. So the first priority is to look at, the call ranges and call numbers, right? A particular book, for instance, if I want to find certain books on like a philosophy and psychology and religion. And so the challenge would be what level of details we want to put into system, like indoor system, so that we can help our patrons to navigate to the right, the book shelf or the stack location, right? And so we look at the Library of Congress classification code, and so we want to stay with like a third tier of the classification, so that we just want to look at the call range rather than actual book location. And so that if you want to find something, the range of BF 501 to 505, that would be a book about motivation, right? And so that's how we're gonna code into our system, or like this kind of hierarchy that we've been building a model to put that or relate that thing with the indoor system. Next slide, please. So that requires to do a thorough kind of survey of the floors, that's especially with the stack locations, their physical location, like cabinets, map cabinets, or like book cabinets, and also like rooms, like study rooms, like meeting rooms, or some tech rooms, and many more, right? And so we started to kind of creating a data layers, GIS data layers, and so map out its stack lines and their different phases, side A, side B, and the starting and starting phase, like the ending phases of those stacks. And not only the physical location of those stacks, but also some of the attributes or like metadata that goes with those stacks, right? So what kind of information that goes within that stack, right? In a particular scene in the middle that you're looking at, one stack that's a stack number 48, and so that call range start from HX to G, and so that the subject area is socialism, communism, and political sciences, right? And so even we try to relate with some of the databases that we have in a library, right? And so that they can they could find some of the resources or some of the ebook, e-material that we features in our online databases as well. And also we try to have some information about subject library and who is responsible for those stacks, so that the patrons who have a question about particular subject area could reach out to the librarian, for better clarification, or to find something and something that's they're looking for. Some of the stacks, they are pretty dense, I mean, in terms of information that goes within the stack. So one picture that's shown on the far right, that's one stack line. There's a multiple subject areas, right? Probably multiple subject library involved to manage those stacks, right? And so we also need to map and validate those stacks line for greater details, or to provide a better accuracy to our patrons. Next slide, please. So we didn't only map the physical location of stacks and cabinets and rooms, but also we looked at all the other POI, the point of interest, right? And so library is not only for books, but we do have other assets type, right? And so some like tech rooms, some even like water fountains, like the copier, like a scanner station, like plotters, and so hand sanitizer station that was needed for this kind of situation, right? And so there are many more the POI category, and so we were able to map around like 221 the point of interest within the Megalodon Library. Next slide, please. So indoor positioning is very crucial in terms of like location accuracy, right? And so we are trying to navigate our patrons within the floors, within compact shelving or compact stacks. And so we want to make sure that we get like a quality, high accuracy location to get to the certain stacks. And so we're talking about sub-meter or meter level of accuracy. And so we started looking into like what could help us to get that level of precision, right? So that we can have our patrons to to find certain things in certain accuracy level, right? And so, I mean, inside the building, we may have like poor Wi-Fi connections or GPS connections. And so we started investigating on some Bluetooth sensors, right? That would help to triangulate the position and then better position the blue dot or like patrons to find certain things, right? Next slide, please. So we looked at a couple of vendors that work with the Arcgis indoor platform, and so this Contact.io is one of the vendor. They work with the Arcgis indoor platform, and so also ASU has like they recommended us to reach out to them, and so we started to try to like do like a piloting with those the sensors, how that what level of accuracy that the Bluetooth beacons would give us to the Megalodon Library. And so we started a kind of pilot for a couple of floors. Next slide, please. So this all project, most of the project was done during the pandemic. So we had like a limited access to building, like a Megalodon. And so we wanted to have like SD folks to come in and just do a better estimate how many beacons we have to buy or how many beacons we need to install per floors, right? So that we can achieve that level of kind of accuracy. And so, they had a travel restriction, and we had a kind of building restriction. And so we had to virtually offer them our floor plans, our floor spaces. And so we started doing a floor inventory. And so we did a thorough picturing of all the floors and looking at the different directions and looking at the different structures within the library within different floors. And so they, based on those photo inventory, they came up with the proposed beacon location that you see in the center picture here. And so the red dots. And so they estimated around like 500 beacons for Megalodon Library for 7 floors. But their proposed location were somewhat like were not appropriate when we look at because they have to rely on CAD drawings and all space inventory pictures. But when we got their proposed location data, and so we look at some of their proposed location, there was some misunderstanding in terms of an infrastructure they saw in a picture, and this what they read from the CAD drawings. And so we had to QC those proposed location and just give them a feedback that some of the location may not be appropriate to mount or install beacons. And so there was like multiple iteration of work to come up with the precise number of beacons to be installed in certain floors. Next slide, please. So so now we came up with like a number of a beacon to be installed in each floor, and so we just started this. Actually, we started this week to install beacons, and so from the Contact.io beacons, and so this process it's probably going to be done for the pilot project by next week, and so we are working on floor 1, 2, and 4th floors. 4th floor, and so we have been mounting beacons and like between the between the stacks, even a wall, and also like there's like a movable stack, and so we are trying to find the fixed stack within the movable stacks, and so we've been tracking, and so you see the picture on the right, that's installation tracking, and so we are done with almost with the 4th floor, and so there's like all blue dots, they are kind of installed and they are up and running. So there's like a few so green dots. There's a problem to where we shall mount the beacons, right? And so we are still working with the Esri indoor positioning system team to figure out the better location to mount the beacons. Next slide, please. So so far, we have done more like prototyping of indoor map viewer or indoor application with the floor plan only, but we haven't started putting all the POI or data that we want to load into indoor system. But we just kind of prototype to see that how the indoor the mapping or indoor viewer works in real in Axon, and so we were able to see the kind of path, right? And so we are looking at the first floor from study room to the cafeteria, and so that gives you a kind of a good kind of routing. And so, but it's still as it's just only floor plan only with some rooms and some other details on the floor plan. But we are still working on getting our data clean and putting into the system. Next slide, please. So this is earlier was just within one floor, and this is looking at across the floor from one floor to another floor, right? And so this is this kind of shows a navigation or like a route from the lobby to my office in the fourth floor. And so, but the 3D view is not that very obvious here, but so we were successfully able to route or set up the route from first floor to like fourth floor or any floor that we wanted. And so that's just to give an idea, that's how the indoor viewer is working on the fly with the only the floor plan data only. So next slide, please. So yeah, the future work, as I said, and so now, so we have all the data cleaned, and we have kind of system configured, like a beacon system being set up for indoor mapping application. So now next would be, we are just trying to build everything, or like a dump all the data that's point of interest, like the stacks and POIs and other data layer that's we mapped in every floor. So it will go into a indoor information data model, and so we'll create a kind of generate a path, and so you're going to be a circuit model path for each floor, and we'll publish that data into indoor portal. And so finally we'll have an application that we need to kind of customize and do some kind of a customization with based on our wayfinding team wish list. Next slide. Just want to thank Gary White, who is a Senior Associate Dean for Research and Academic Services, who initiated this project and made the funding available for this project. And so we also like Taylor Keene and Rocky from Enterprise GIS. They've been great help to set up the things and help us with the field work and prototyping and reaching out to Esri and working with Esri indoor team and Esri technical support team. And so also libraries, technical IT staff. And so I'd like to thank my GIS staff, Manal and Jameen. And so Manal did lots of kind of field work to map and inventorize all the assets and POI within the floor. The next slide probably is, if you have any questions, I'll be happy to answer.
Any questions for Milan? This is a very interesting project.
Thank you.
I have a quick question. So from the user perspective, do they need to download the Arcgis indoor app?
No, so it's going to be a kind of an application. And so we're going to build an application that's going to embed Arcgis indoor within the application. And so they have to download in a certain application though. And so we also thinking about a kiosk on the first floor, and so even they could log into a kiosk and find the things that what they want, and so they could that would show the path or kind of route to their destination.
Cool, thank you. I have a question from the chat. Is there a method for users to report errors?
Yes. That's been a kind of priority because the things may change over time. And so like especially stack. So also like some of the, even we mapped some of like trash bins or recycle bins, right? Those are kind of movable assets, right? And so yeah, we do have like, that's kind of where we're gonna do a customization, like build like a GUI that user could provide a feedback, right? And so even if they're looking for a book on certain certain topic, right? If they can, if that app takes you that to the particular location, but they don't find the thing that you're looking for, and so they should wait to report that kind of error to us, so that we can adjust the database, or we can recreate the route. And so that's we plan to update and recreate the route every beginning of the semester or so. Yeah.
Any other questions?
I'll ask one quick question if we have time for it. This is like, it seems like such a great project that so many libraries could do and could learn from what you're doing. Do you feel like it was where did the motivation for the project come from? And was it kind of a hard sell? Because it's a lot of resources to pull all this together.
Yeah, I mean, the thing is that there's always this kind of challenge. Like I was onboarded in this, I came to EMD maybe almost 1.5 years ago. So they started thinking about the project, and so they always had a complaint from the users. So they couldn't find the things that you're looking for, right? And so things that you point out in the paper map might be outdated, or the things that might have changed, right? And so they need some kind of robust way to centralize the resources and reporting system, right? And so my approach here would be like, because there's like too many entities like handling those like a signage, like paper map, and like working on the stacks. And so there's a kind of different siloed, I guess, and so they never kind of sync together in terms of kind of reporting, and that end up being kind of wrong information to user at some point. And so the idea of the project would be to also centralize kind of reporting system by different entities, so that we are in the same understanding when things are updated. And so we're not updating only our signage, but we're also updating the things that goes within the stacks, or goes within certain things that we update on the floors. And so yeah, I mean, it was a lot of like surveying of the assets, and so the data creations, and so like cleaning up data. And so there's a multiple iteration, and we have to do the QC of data, because some of the project we started, they started maybe 2 years ago, and so things might have changed before pandemic and after pandemic in terms of like relocating some of the stacks, and also the spacing out some of the study rooms, right? And so that's kind of sort of idea that we we wanted like come up with like some kind of a centralized system, and also better navigation, so that we can have our patrons to route and to find the things in a timely manner. Yeah.
Thank you. Glenn, you have a question? You can speak up.
Yes, I was curious about these beacons. I believe you mentioned 700 some. Do they each need to have a location configured, or are they just placed and they work from there?
Yeah, so the way the beacons need to be triangulated, right? And so at least we need for better positioning, we need at least 3 beacon talking to that blue dot, like to the patrons app. And so that's what we have to like install in such a way that there's a certain like an antenna kind of facing to those kind of 3 beacons at the time, like in a certain location, right? And so that's there's a certain the positioning, or like a number that has to go within the floors based on how compact or how dense is your floor with the other structures, right? And there will be too many columns or too many stacks, right? And so based on that, and so we have to come up with a number. And so they came up with the estimate, and so still we try to put more beacons than they estimated, because we know our floors better than that they've been surveying, kind of virtually looking at it. And so we try to put more beacons than estimated.
Thank you, Milan. I think
Sure.
we're at time, and we'll move on to our second presentation. So our second speaker is Jon Schwichtenberg. He is a GISP and a GIS leader for GRAEF, an engineering company. Jon has been working in the GIS and asset management field for over 30 years. He has developed the systems, implementation for clients, managed system for clients, completed fieldwork, cartography, and much more. Jon will be talking today about integrating drone data into GIS systems and current day engineering for building exteriors. Jon, I'll pass it to you and I will start sharing the slides.
Awesome, thank you.
Give me a minute.
Yeah, so I'm going to talk a little bit today about how we are using drones for doing facility assessments on different types of campuses. That's fine, you can leave it at that. At the next one. And you know, we've been integrating drones a lot into a lot of what we're doing from an engineering perspective on buildings lately. And as said, I'm the GIS leader for GRAEF. GRAEF is an engineering company. We're about 270 person firm, so probably about what I'd say is a medium-sized engineering company. I've been working in the field for, you know, you can see the gray hair. I've been working in the field for about 30 years now. I actually do a lot of teaching as well, teach a lot of training sessions and do a lot of training for a lot of different organizations on these subjects. Ultimately, what we really are doing is taking all of the data that we're collecting and everything and putting it into management systems for our clients so they can actually manage their buildings long term. You can go on to the next slide. The data collection though has become really automated with using drones. There's a lot that goes into that, you know, to be able to collect data on campuses, and campuses could be, you know, medical facility campuses. It could be just large companies that have large campuses. We're actually doing this right now on 19 different buildings at the University of Wisconsin in Madison. So we're applying that to the education campuses as well. But what you have to be concerned with when you're talking about drones is not necessarily you know, the actual drone itself, but where you're at, where your facility is at in comparison to a lot of different things. Airports for one, you have to do a lot of public planning. You can't just go out and fly a drone at a building or a campus for that matter. If you're within a certain area from airports, you actually have to file a flight plan and file and get FAA approval for using the drone. And you know, we're actually talking about pretty high tech drones. I mean, this isn't the typical drone that you can just go buy for a couple $100, you know, at the store. So these drones actually, you know, are anywhere from $15,000-$20,000 all the way up to hundreds of thousands of dollars. The more expensive part actually is the camera, and I'm going to talk a little bit about the different cameras that we used or use on our projects. But ultimately, what we're trying to do is gather the ground data, gather the data of the actual facades or the sides of the buildings, so the windows, the brick or whatever that facade might be made of, and then roofs as well. Roofs are kind of a different animal, and I'll talk a little bit about that. But ultimately, you know, we're getting really good base data for the entire campus. You can go on to the next slide. So from a grounds perspective, you know, obviously when you fly a drone and you're talking about integrating all of the flights, the photos, this is actually a photogrammetric process. So there was about 3,000 photos that were actually gathered in this flight for this campus in particular. And then they're all stitched together from a photogrammetric perspective. And you get accuracy based on what your actual ground control is. So in this case, we had a lot of ground control and the ground control was picked up with a centimeter accurate, survey accurate GPS system. So all of the data relative to itself then turns into a centimeter accurate campus model. So you don't not only have the actual photos and the data that we're collecting, but you're also getting a 3D mesh and 3D model that goes along with it as well. And then you can see the other picture here on the screen. You know, we can actually then pick up all of the data that goes along with that on the campus, whether that's trees or buildings or whatever that might be. So there's some ancillary benefits of not just the buildings themselves. You can go on to the next one. From a roofing perspective, what we're doing is we're getting really high resolution pictures of the roof. So there's a couple of images here on the screen. You can see one is a thermal image and the other one is a regular image. The regular images are literally, you can zoom in and actually do measurements of cracks or measurements of an area and get very accurate data from those images. The thermal actually gives us an idea of where there's leakage. In the case of the image on the screen, there's actually some displaced ballast. So what happens is with the ballast not being properly placed, we're actually losing heat loss. We're having heat loss on the roof itself. So we're actually able to collect that. And then again, those images are very accurate. So we can actually measure those and actually even put quantities to that as well. Now, typically when we do a roof inspection, we're actually going up and coring the roof to try to find any areas where there's wet areas or there's insulation is bad. And we're actually doing tests on those cores. With this process, we don't have to do that destructive testing. So that actually allows us to just fly the thermal imaging and do some thermography with it. And in this case, this project, we actually brought in a national thermographer that actually works with the federal government as well and does a lot of this throughout the United States. And by doing that, they actually find the areas then for us and are able to map them. Then we take them into the GIS system. And the other part to this too is we actually are able to then put cost estimating to it, severity. We actually do severity indexing, and occurrence. Is the roof likely to fail because of this? And then we actually are able to put all that into the GIS system and then manage that data. You can go on to the next slide, please. We're doing the same thing from the perspective of the facades. With the facades, though, we're actually looking from a thermography perspective, we're actually looking for something more than what we're looking at on the roof. We're actually looking for cracks. So you can see here on this image, some of the windows are actually leaking, as well as there's a major crack where the two brick areas come together. There's actually some leakage there, but then in the wall itself, we're actually seeing a spot where there's most likely a moisture issue. And that issue is probably coming from that window bank above it, and it's probably leaking down through the wall and creating that moisture issue. We wouldn't normally find that when we're doing a facade inspection for a building from an engineering perspective. We would find cracks in the walls. We'd find other things that are actually wrong with the exterior of the walls, but we wouldn't find that moisture issue, which is a plus from the perspective of doing this with the drone and actually getting the thermal imaging. You can go on to the next slide. So we're engineers, right? So engineers analyze data, right? So a big part of what we do with this drone information is we're taking the high res imagery and we are actually doing our engineering analysis. In this case, this is a smokestack, and we're looking for why the smokestack is about to fail from a structural perspective. And what we've found in this case is there's a lot of cracks. It's not really structurally sound at this point anymore. and we're, you can see from the image of the severity and the occurrence and the detection that there's not an obvious problem. Failure is inevitable. I mean, it's going to fall down if it's not taken down. So, through that analysis, again, we're able to use the GIS system to document all of that, as well as document the costs and get an accurate budgeting perspective for them as well. You can go on to the next slide. Part of the reason that we're doing this inside of a GIS is that from the exterior side of the building is that there's so much you can add to the interior from the interior as well. So when we're doing inspections, we're talking more about the drones right now, but what this allows us to do is integrate the exterior from the drone inspections with the interior inspections as well, and look at life systems, the electrical, fire protection, HVAC, all of that, and holistically be able to manage the building itself. So you can go on to the next slide. And from the exterior, from the site itself, we also add, hard parking surface areas. We can do analytics on the surface parking and see where there's need for revamping, or redesigning, redoing the parking lots. Same with sidewalks. Stormwater becomes a piece that we can add into the campus here as well. So again, ancillary things that we're getting because we're flying it with the drone and actually getting that high accuracy data as well. But we can then pull in all this other data and manage it inside the system for them too. Go on to the next slide. Obviously, the things that we find with the drone, then we want to be able to track, when does it need to be repaired, what needs to be repaired. There's photos that are attached into the system, so we know and understand what all of that is. And then we can also use this to track not only the cost and the budgeting, but we can track, there's going to be a consultant that goes in and does the construction and fixes the issues. So that consultant then can use that same system to document that, and then the owner and the engineer at the same time can be doing construction administration right inside of the system from a digital perspective as well. Again, kind of trying to automate what we're doing from that perspective. Go on to the next slide. So really what we're trying to do with all of this automation is trying to make sure that the client has a way to manage their facilities long-term and give them that ability. And that's several things, actually managing the building itself, being able to update the information, use it for budgeting purposes. Everybody knows that, you can't just budget $10 million worth of fixes in a building. You have to do that over time and base it off of, failures and what's going to happen with the building, so you can continue to keep the building going. And then long-term capital management, actually knowing what you have to do from a maintenance perspective long-term as well. So go on to the next slide. This is actually a really super unique project these pictures are from. And this is actually the state capitol building in Madison, Wisconsin. And there's parapets that are on the exterior of the building, and all of the exterior of the roof it's all granite. So what we have to do is we actually have to have somebody on tethered on ropes on the outside of these buildings doing inspections. So in the past, we've actually done the inspections just with people, right? You haven't had the technology, the ability to do it from a perspective of drones. But now we can actually do it from a drone perspective and fly the drone, get the pictures, and do the engineering and the analytics actually sitting in an office rather than having specialized people actually out on site doing the inspections. So again, we're looking at it from a condition data perspective, trying to make the life cycle of the building as long as possible in its current state. Obviously, you're not going to rebuild a granite roof on a state capitol building. And we want to make sure that we maintain that, and that, you know, that there isn't failure, because if there is failure, then, you know, you have a very major building that would no longer be able to be used. So again, criticality and life cycle is very important when we're doing these. Move on to the next slide, please. Again, one of the other big things that comes out of this is being able to do capital budgeting then from the facility perspective. And, you know, generally speaking, you know, we're trying to keep records for digitally for as much as possible, so that they can manage that data, do master planning, get an accurate estimate then into the system. A lot of times we'll bring in actual people that are construction companies that are doing the estimating, so we actually get true estimation. And then be able to do projections long term and what that building is going to need. Move on to the next slide, please. Well, that's my presentation. If you have any questions, I'd be happy to take them. Otherwise, there's my contact information too. You'd be more than happy if you wanted to reach out and ask me questions later as well.
Thank you, Jon. Any questions? I have a question about, I think in one of the slides you showed that you use the thermal image to detect the moisture.
Yep.
Does it mean it works better than like detecting by eye? Like it's better to use the thermal image?
Yeah, so you know, it's with a building exterior, for instance, you know, roofs are a little different, but with the building exterior, we do engineering inspections of, you know, the actual exterior, where you're going to find cracks and other things. You can actually do inspections of the exterior of the windows too, and actually see glazing that's bad and other things like that that would tell us that there might be a moisture issue there. But without the thermal, we actually don't know the extent of that, right? And with the thermal, we actually get to see the extent of those things, whether that's heat loss, because the glazing's bad on a window, or like the one example I showed on the screen actually had some moisture issues about 2 feet underneath of the window. And that's likely caused because the glazing's bad and there's actually moisture coming through the window into the wall itself. We would never see that unless you know, had mold or something on the interior of the building that you could physically see, but you would never really see that otherwise. So the thermal actually gives us a lot better inspection of the building, and actually gives us a lot more data that's real for us to go back to the client and talk to them about their issues.
I see. Thank you. I see we have some questions from the chat. Have you run into any issues with drone restrictions?
Yes. So, I mean, so there's a couple things. There's a lot of different drone manufacturers out there. And depending upon who the client is, there's only certain drones that you can use. And that's one restriction. The biggest restriction is from an air perspective. I mean, if you're anywhere near an airport or flight lines, you know, there are some restrictions with that. The one hospital that we just showed, they actually had a flight for life on site. So we had to actually coordinate with that as well. I mean, obviously you can't have a drone in the air when there's a helicopter that's either coming in or going. So we actually were on walkie-talkies on a consistent basis with that team to make sure that we weren't interfering with that. But one of the biggest ones is the FAA. You know, actually knowing where you're at in the world, and kind of if you're in a flight line, how high you're going to need to fly, and actually putting together a flight plan so that you understand and find what those restrictions might be ahead of time. So.
We have another question. Do you anticipate when the next reasonable time would be to do another extensive drone flight? I imagine there might be times to check on specific things, but this is more about a whole campus update.
Yeah, so it from a building perspective, obviously, you want to check, probably refly that thermal, at the very least the thermal, probably every 3 to 5 years typically. You're going to have a lot of things that are changing over time inside your buildings. If you're adding new buildings, obviously newer buildings, you wouldn't necessarily have to fly. Maybe you could eliminate that for 10 years. But it kind of depends on the campus itself. And then from the perspective of if there's a lot of change on campus, it doesn't hurt to fly the campus, every couple of years and look at the change. The nice thing about it is, by doing that, we can actually just look at the images side by side and actually do some comparisons to quickly take a look at any change over time. So the new flight the flight itself would cost the same as the old flight, but the analytics time would be dramatically reduced. So.
And another question, could you speak briefly about photo registration part, the systems and methods you're using for registration of the drone photos using the ground control points and the 3D modeling part?
Sure. So it is a photogrammetric process. So you're literally stitching together the photos. You're then creating a mesh from your flight, and that mesh then is registered with all of the ground control points that you've taken, and then the mesh is actually what's used to locate all of the actual photos. So to the side of the building, create the 3D model with all of those photos attached to it. In the case of this, we're actually using a couple of other products that actually take those and pull all that information together from a 3D perspective, and then create links. But then what we did is out of that process, each photo then is registered actually where it's at, and it's given a geotag. So then we're able to take those geotagged photos, pull them into our GIS product, and that GIS product is an Esri product, but we're able to pull it into the GIS product and actually put it in the real world where it is. So it's actually located correctly from the center of the photo, and then that photo link is attached so that you can click on those points and actually bring up the photos. So everything is geo-registered. And again, it just kind of depends on your ground control, the accuracy of that, the accuracy of the actual flights, so there's a lot that goes into it to determine kind of the accuracy and locational aspects of everything. But in this case, technically it's relative to centimeters. It's not centimeter accurate to the world, but it's relative to all of the data. It's centimeter accurate on the campus.
Any other questions?
All right, thank you.
Okay. Yeah, thank you. So we'll move on to our next presentation. So our next speaker is Glenn Vorhes. He has 10 years of experience working at the Conference of Engineering, GIS, and Computer Programming. He has been working with the Traffic Operations and Safety Lab at the University of Wisconsin for the last 6 years, where he specializes in data management and creation of analysis and visualization tools. Me start sharing my screen. So Glenn, you can get started.
Yes, thank you for the introduction. Welcome to my presentation, Low-Cost Connected Work Zone Devices with Simplified Architecture. I'm presenting this in the context of work zone, construction zone monitoring devices, but I really think these can have applications in other disciplines. Connected devices in road construction work zones are becoming increasingly common. I'll define a connected work zone, a connected device, as one that transmits information from sensors or communicates device status to a remote location. A few examples that I'll be discussing include cones, barrels that report their location, traffic control arrow boards that indicate the direction status, impact sensors mounted on barriers, and traffic speed and count sensors. As this is a GIS conference, all of these have a spatial component where the device status or monitoring is tied to a point location. I was missing the, next slide, please. And one more. There are some limitations in the approaches to date, but the biggest among them is the cost. Many devices can cost thousands of dollars each, and that's only for the equipment. There are also connectivity concerns. A typical connected device will have a dedicated cell modem to connect with a central server, and that comes along with monthly data charges, and that's assuming coverage is available. Most areas now have cellular data coverage, but rural regions might not. And beyond that, the central server needs to have configuration for each device, which increases the complexity. Device vendors handle this by managing the device connections and data transmitted that is then exposed by a proprietary API. This makes things easier for the data consumer as they only need to interface with a single source for multiple devices, but introduces data ownership concerns. Vendors might provide a real-time data feed, but archived data is retained and only available at an additional expense. The goal of this effort was to create devices from inexpensive components. There's an abundance of possibilities from low-cost sensors and microcontrollers, along with capabilities of hobby-level programmers. Viable monitoring devices can be created for tens of dollars rather than hundreds or thousands. To simplify the architecture of the system, many individual devices communicate with a central point of contact within the work zone. Next slide, please. This is starting at the lowest level of the individual components. They will use a GPS receiver, an accelerometer, a directional LiDAR unit, and a small LCD screen as a substitute for an arrow board. Next slide, please. A microcontroller is a simple device to interface with sensors and other devices. It is not like a computer in that there's no user interface, just two programmable routines. There's a setup function that runs once, followed by a loop function that runs continuously. The most well-known hobby-level microcontroller is an Arduino, but we chose an ESP32. This has 3 serial ports for interaction with devices and sensors. That's a big advantage over a typical Arduino that might have only 1 or 2. But beyond that, the ESP32 has built-in Wi-Fi and Bluetooth for a cost of around $5 per unit. Next slide, please. Long range, or LoRa, as it's called, is a low-power, long-distance radio transmission method. These units can transmit over long distances, but very slowly. The device shown here is just one implementation of LoRa and works on the unlicensed 915 megahertz band. It has 1 serial port to interface with other devices. Information is passed as text from unit to unit. The data transmission rate is configurable with a default speed of 2400 bits per second. The claimed range is 8 kilometers under ideal conditions, meaning line of sight and no interference, so the effective range is less. There are 4 transmission modes. For our purpose, we used fixed monitoring where several nodes transmit to a single base. Next slide, please. The ESP32 and the LoRa are challenging to work with individually. So we created a unit that combines the two along with some complementary components. The first, configuration of the LoRa, such as the channel, transmission mode, and target device, is done by means of an app that we developed to communicate settings via the Bluetooth connection on the ESP32 that are then passed to the LoRa. Serial port 2 can be connected to anything communicates with a serial port. Examples could be Arduinos reading and processing sensor inputs, a Raspberry Pi, or a computer using a simple USB to serial adapter. Our use case was for monitoring devices in work zones, but this unit and a simple configuration and hardware interface could be easily adapted for other purposes. And next slide, please. To the second part of the presentation, the simplified architecture. Integrating inputs from tens of devices in the field can be challenging for a central server. The managers need to keep track of individual devices to process the data received from them. I present an alternative where multiple devices communicate with a central base location. This assumes that each device communicates a unique identifier or location information along with any monitoring results. The data received at the base could be logged directly for later processing. Another option is for the data received at the base to be passed to an internet-connected device that in turn passes it along to an application server. In this way, tens of individual devices can communicate their results over a single internet access point. Next, I'll talk about the application server and an example client application. And go ahead. A web application was created to support the project. The server component was developed with Python and the Flask web framework. In a typical web application, the client initiates interaction with the server and receives a response. With WebSockets, two-way communication is enabled between the server and the client, which then lends itself to real-time applications. This application has only two endpoints. The first is a data endpoint. Data submitted as the D parameter is received and passed along to any connected client applications. The second returns the page seen in the image here. The client application was developed using open layers in React. The application responds conditionally based on the format of the data received by the WebSocket connection. At a minimum, the data is logged in the write pane and adds stylized points to the map based on the format of the received data. And next slide, please. The first field test was to confirm that data could be reliably transmitted in real-world conditions. The stated range of the LoRa was 8 kilometers, but that was with line of sight and no obstructions. Highway 12 in Madison served as a test location. A rover unit mounted on a vehicle transmitted its coordinates every 2 seconds over the radio link to a base station at a fixed location. The vehicle was driven 8 kilometers east and west of the base station beyond the expected transmission distance. Any points logged at the base were those that were successfully transmitted from the rover unit. There's an inverse relationship between the transmission speed and the viable distance. A range of transmission speeds were tested. As expected, the longest transmissions were seen with the lowest speed and more gaps in reliable coverage and higher speeds. But at 2400 bits per second seemed to be the best compromise. And next slide. Several prototype devices were created. Components to all include one of these ESP32 LoRa units, a microcontroller, and a GPS receiver. The connected or location-aware cone includes only those components and nothing more. Arrow boards are common features in work zones. They show an arrow to indicate that a lane is closed. A connected arrow board communicates its status and location. A small LCD was used to represent a full-size device. A connected portable message sign would work similarly. An impact sensor includes an accelerometer. When subjected to a shock, the impact sensor will report its location. And finally, the traffic or queue detector uses a directional LiDAR sensor aimed laterally across the lanes. An Arduino is programmed to continuously monitor the distance and use a simple algorithm to count vehicles and determine speeds. Next slide, please. Here's a schematic of the device test. The base station receives data from the devices over the radio link and passes it to a Wi-Fi connected ESP32 that in turn sends it to the application server that then notifies any connected client applications. The 4 prototype devices are shown with the data structures they transmit. For example, the location-aware cone transmits its status as a comma-separated pair of coordinates, an asterisk, the word cone, another asterisk, followed by a unique device ID. Next slide, please. The proof of concept was successful with the prototype devices sending data by radio link to the base all the way through to the data display on the monitoring dashboard. The point features appeared in real time during the device test. You notice the points with the location-aware cones, the connected arrow board locations and statuses, the impact sensor points, and the traffic count information presented in a pop-up. Only 4 prototype devices were created in this test, but the number of devices could be easily scaled up using the same infrastructure and at minimum cost. Next slide, please. On the topic of cost, keeping the device cost was one project goal. All devices described have an ESP32 unit with a total cost of around $20. Adding a microcontroller and a GPS receiver takes the cost to around $40. From there, the low-cost sensors can be used to create the prototypes described for sensors for other applications like environmental monitoring. The most expensive single component in everything described here was the LiDAR unit at around $42. These devices were intended to be used where AC power is either not available or would be too expensive to install. The units use the most power when the radios are transmitting and much less in an idle state. Depending on how much data is transmitted or how frequently, these devices could run continuously on a small battery pack or permanently with the help of a modest solar panel. Next slide, please. This project has shown that we can obtain valuable data from devices costing tens of dollars rather than hundreds of thousands by leveraging the components and skills used by the maker community. The low cost lends itself to higher sensor density for a more accurate picture of real-world conditions. The use of data radios and a hub architecture reduces cost and complexity. There can be as few as one internet connection point serving tens of sensors. We also avoid integration and data ownership concerns with proprietary platforms. The next steps include improving security. An updated model of the radio unit includes something akin to a password encryption, but tests will be needed to confirm it's safe for use in a work zone monitoring application. Other than that, I'm looking to scale up the number and types of devices. The 4 prototype devices worked as expected, but I'd like to see 10 or more deployed in a semi-permanent way rather than taken out just after a day. That will give us a better idea of the viability of low-cost devices with a hub architecture for work zone monitoring or other applications. And with that, I'll take questions.
Thank you, Glenn. Any questions? I have one question. So you mentioned there is a special component in this project. Could you talk a little bit more about how this help?
I'm sorry, say that again.
Oh, I mean,
all the devices have a location in addition to a status or some event. For example, an impact sensor based off an accelerometer receives a shock, and it transmits that information. It transmits both its location and that something occurred over the wireless connection, and that can then be presented or either on a map, or appropriate alerts could be sent to emergency responders.
Okay, so you're planning to have a map of all of these sensors, like the locations?
Yes. One thing that I wasn't sure if I would have time to show. Is it possible for me to share a screen?
I think I got that for you. Let me just bring this up. I got that link. Share my screen. That's the website.
Yes, it is. So what you're seeing here is this is the live application. It's receiving. I have a Python script running in the background that's submitting to the data point, the second endpoint of this application, and what you see coming in on the right pane is it's information that's added to sent to the data endpoint. So I'm on here right now. So if I hit something, you see that test 3. That was me sending something to the data endpoint. So it's a real-time feed. There's information being sent to the data endpoint that's then passed along to this connected client application, and the point information is displayed there on the map. Hopefully that explains more about the spatial component of the devices I've described.
Yeah, that really helps. This is really cool. Thank you.
It's running now. It's just a matter of this secondary Python script in the background, just for the sake of today's presentation. And this will be really boring once I turn that off. No data will continue to be displayed.
Okay.
Any other questions?
Just curious, the Gillian. So you're looking at your animation, and so you have a real the time and the data, right? And so how you think, like, how you're going to manage those kind of real-time data, right? It's going to be a massive data. So when you do kind of other prototype, and so do you have any kind of workflow, a plan for like a data management on the back end?
Well, you know, that's kind of the nice thing about the way things are set up. That's more or less taking care of the same application as it exists now. It could receive the inputs from any number of sensors. This is just one potential application here. Right now, the data that's being submitted to the data endpoint, there isn't any additional processing at that level. All it does is pass it along to this client application that responds conditionally. So it sees it coordinates a star, a cone, and then star 5. And that's an indication of yep, that's one of these like location-aware cones. So the server-side component of this is really simple right now, but that said, it could be extended to and incorporate or support any number of devices in the field.
Yeah, I mean, just curious, especially when you have like a LiDAR sensor, right? And so you're going to be a kind of continuous scan, right? And so, and that may create a trouble at some point.
Yes,
a random thought. So
yes, that's a good point. So in the field, these devices, they have their own implementation. The LiDAR sensor, for example, it's a directional. The one we use is a directional unit, updates 100 times per second. Now that said, it does not submit results 100 times per second. So it's aimed laterally across the lane. Think of a car passing by. It'll count that car and determine a speed, and that's all it'll send into this application. It won't send the full data set, the raw sensor data. That you're right. That would be too much for the system.
interesting. Great. Thank you.